Section 2.2 is some of the rules for differentiation. Quite honestly, this is a foundation for the next several sections, in fact, next several chapters of this class, calculus. So this is one of, if not the most important section for you to absorb. You cannot get out of this section without understanding and being able to use each one of these rules on hand from memory many times. So very, very important foundational section that you have to be able to do here. I did assign you homework and quizzes out of this section, but I cannot express what I assigned is not enough unless you have it down cold without referencing your notes. So please spend extra time on your homework, spend extra time doing extra problems for this section. It is absolutely vital that you understand this section for the remainder of the class. So what we're going to do is learn some tricks to differentiation. We learned in the previous section that the derivative is the same thing as the slope of the tangent line, which is the same thing as the slope of a graph at a point. And again, when we find a slope, we usually need 2 points, but here we're not finding the slope between 2 points, we're finding the slope of a graph at a single point, and that's called the derivative. Okay? So what did we learn for finding the derivative? We learned, and I'm gonna highlight the one that I did. We learned that the definition of a derivative comes from finding the slope between 2 points. In particular, we chose the point x and x plus h. And then what we did was we moved those 2 points closer and closer together. And since the difference between them was h got smaller and smaller and smaller. So that gave us the limit as h approaches 0. And then this top here was our change in y values. And the bottom here was the change in x values. So that's where that formula came from. The limit as h approaches 0 of f of x plus h minus f of x all over h was the slope between 2 points, where it was x and x plus h, and then we brought those 2 points together. So this is the derivative. And the way that we write the derivative most traditionally is f prime of x, okay? Again, if you are using the book, they're going to use delta x and say as delta x approaches 0, I just use the letter h. But the idea is this limit process is a pain in the butt. It takes forever. So can we learn some tricks so that we don't have to do the limit process? And the answer is yes. We can learn tons and tons of tricks. So we never have to do the limit process again unless the problem specifically asks to use the limit definition or the definition of a derivative. We will not have to do limits after this section, which is really nice. So the first rule that we want to learn is the constant rule. What's a constant? A constant is just a number. So I want you to consider, I'm going to do this graphically and then I'm going to do this using the definition of derivative like they liked, but I want you to consider the function f of x equals 5. In other words, y equals 5. And let's think about that. What we would have if we looked at the graph of this is y equals 5 is a horizontal line at a y value of 5. Your y value is 5, your x values never change. So every single y value has to be 5. I want you to think about that. Again, we said the derivative is the slope of the line. Well, if you did the the lines and functions review, you would remember that the slope of any horizontal line is 0. And if the derivative is the slope of the line, then the derivative should be 0. So we should get a derivative of 0 here, meaning the slope of any horizontal line is 0. And notice, y equals 5, the fact that it was 5 didn't matter. It could be f of x or y equals any number. It's always a horizontal line, so the derivative should always be 0 for any constant function, no matter what. But let's go ahead and do what they wanted. They want us to use the limit definition of the derivative. So we're going to look at the limit as h approaches 0 of f of x plus h minus f of x all over h. Well, in this case, that would be the limit as h approaches 0 of f of x plus h. So anywhere I see an x in the original function, I'm going to plug in x plus h. Well, there is no x in the original function. The function is just 5, so that would be f of x plus h minus f of x. Well, what's the original function? The original function is just 5, and that's all over h. So that's f of x plus h minus f of x all over h. Well, notice 5 minus 5 is 0. So what we really have here is the limit as h approaches 0 of 0 over h. And 0 divided by any number is just 0. We do have a number on bottom, so it's not undefined. So this is the limit as h approaches 0 of 0. And the limit of a constant is that constant, so the answer would be 0. So what did we just say? We just said f prime of x, the derivative of 5, f of x equals 5, is 0, which is exactly what we saw when we did it graphically. The derivative of a horizontal line is 0. We just did it using the limit definition. And again here, I want you to consider doing this problem. It doesn't matter what the constant was. In this case, the constant was 5. No matter what the constant was, think about that numerator. If it were negative 10, it would be negative 10 minus negative 10. If it were square root of 2, it would be root 2 minus root 2. No matter what it is, that numerator would be 0, making the term 0, making the limit 0. So no matter what it is, no matter what the constant is, your derivative is 0. So let's look at the next problem right here. It says find the derivative of constant functions using the constant rule. The constant rule being what we just determined, that the derivative with respect to x of any constant is 0. Or you could say f prime of x when f of x equals c, any constant, equals 0. Okay? That's the constant rule. So look at this. Here's f of x equals negative 2. What's the answer? The derivative would be 0. We do have to show work. What's the work? Just simply write the word constant because it's a constant. Same thing. How about the number pi? Pi is also a constant. Pi is a never-ending number. It's 3.14159. So on, so on, so on. It doesn't matter. It is a constant, so its derivative is 0. We do have to show work, so I'm just going to write constant. In fact, it's the same thing with all of these problems right here. How about the square root of 5? Square root of 5 is an irrational number, but it is just a number. So again, its derivative is 0. It's a constant. Same thing with d. S of t equals 320.5. Again, this is a number. The derivative of any number is 0 because it is a constant. It would represent a horizontal line, and the slope of any horizontal line is 0. Okay, now it says, now use the definition of derivative to find the derivative of the following functions. See if you notice a pattern. So what's the derivative of 0? Well, 0 is a constant, so its derivative is 0. We already know that one. We've already done it. But I'm going to go ahead and on the side here, I'm going to do the derivative of each one of these, x, x squared, and x cubed, using the limit definition of the derivative. So I would suggest getting out an extra piece of paper or doing this on the back page, the back of the page or something like that, because this is going to take some work. Let's look at this. Let's consider f of x equals x, the original function f of x equals x. Well, if I want to find the derivative of the function, I'd have to do the limit as h approaches 0 of f of x plus h minus f of x all over h. So in this case, that would be the limit as h approaches 0. And now I'm thinking wherever there's an x in the function, I'm plugging in x plus h. So that would simply be x plus h minus the original function, which is just x, all over h. Well, notice in the numerator, we have the x's simplify. I know you probably want to simplify those h's as well. You cannot yet. You have to do it in a complete separate step. It has to be done in 2 steps, or it's not mathematically accurate. So now we have the limit as h approaches 0 of h over h. The h's simplify into 1s. So this would be the limit as h approaches 0 of 1. Well, the limit of a constant is that constant, as we learned in a previous section, so the answer would be 1. So what did we just learn? We learned that the derivative with respect to x of x is 1. Let's go on and look at the next one. How about x squared? How about g of x equals x squared? So if we want to find g prime of x, we would be looking for the limit as h approaches 0 of g of x plus h minus g of x all over h. I just gave it a different letter so you don't confuse it with the one above it. So this would be the limit as h approaches 0. And now again, instead of just an x, we're going to be plugging in x plus h. So that would be x plus h quantity squared minus the original function, which was x squared, all over h. Again, if you think about it, what happens if we plug in h equals 0 now? Well, this would be a 0, so that would be x squared minus x squared. This would be, the numerator would be a 0. The denominator would be a 0. 0 over 0 is undefined, so we can't just plug in the number. We need to do some math. So what I'm going to do is I'm going to FOIL out that top. The limit as h approaches 0. X plus h quantity squared. Remember, you have to FOIL that out, so it's x plus h times x plus h. When you do x plus h times x plus h, you would get x squared plus xh, which would be 2xh plus h squared. That's the x plus h quantity squared. We still have that minus x squared. Don't forget that in the numerator. And this is all over h. Notice what happens in the numerator. We have those x squareds canceling, so I'd be left with the limit as h approaches 0 of 2xh plus h squared all over h. I notice that the two terms both have an h in common, so I can factor out an h. So this is the limit as h approaches 0 of h times, well, let's see what happens when we factor out an h. If I take 2xh and I divide it by by h, I'd be left with a 2x. And if I take the h squared and I divide it by h, I'd be left with plus h. So that's the factored version on top. We have an h on bottom. Why did we do that? Because now the h's simplify. So what am I left with? I'm left with the limit as h approaches 0 of 2x plus h. Well, that's simple enough to plug in our limit. Anywhere we see an h, we're going to plug in a 0. Notice I've been writing the limit as h approaches 0 every single one of the steps until this step. This is the step that I can finally not have to write limit as h approaches 0 because I'm actually plugging in 0 for h. And that would leave me with the answer of 2x. So what's the derivative of x squared? The answer is 2x. The derivative of x squared is 2x. Okay. I do want to take a minute to just say, again, in the last section, I taught you how to find the definition of a derivative. In many of the examples, I did multiple steps. I did like a 4-step process where you first find f of x plus h, and then you subtract off f of x from that and simplify, factor out an h, and then you divide it by h, and then you find the limit as h approaches 0. So it was like 4 steps that I was doing in the previous section. If you're not comfortable doing it all at once, like I did right here, please go back to those 4 steps from the previous section. You will get the exact same answer if you do it using those 4-step method. I just like doing it once I get better with it and more comfortable with my algebra. I like doing it all in line at once. It's essentially the same steps. It's just a little more organized, and I can put equal signs everywhere. So this is the way that I like doing it. If you like those 4 steps, please feel free to do it. All right, let's keep on going. We're going to move on to the last one that we're asked to do by hand, which is x cubed. So let's find the derivative with respect to x of x cubed. So again, that would be the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so that's equal to the limit as h approaches 0 of, well, anywhere we see an x, we're going to plug in x plus h. So that would be x plus h quantity cubed minus the original function, which would be x cubed all over h. All right, so this is going to take some work. You might want to do some side math here. I'll do it in blue. When you look at x plus h cubed, well, that's really x plus h times x plus h times x plus h. So we got a lot of foiling that we need to do. I'm going to multiply these two out first. That would be x plus h times, well, if I multiply those two out, I'd have x squared. Then I'd have plus xh plus xh, so that'd be plus 2xh. And then I'd have plus h squared. So that's me foiling out those first two. Now what I'm going to do is I'm going to distribute this x plus h into those terms. So I'm going to multiply x times everything, and then I'm going to multiply h times everything. So let's do that now. I would have x times x squared is x cubed. X times 2xh would be plus 2x squared h. And then x times h squared would be plus xh squared. Now I'm going to distribute the h through to each one of those terms. h times x squared would be plus x squared h. H times 2xh would be plus 2xh squared. And h times h squared would be h cubed. So that's what it looks like when I FOIL it out. Let's see if there's any terms that I can combine. I see here's an x squared h term and here's an x squared h term. I see here's an xh squared and here's an xh squared term. So combining them and simplifying, I would have x cubed plus, looks like I'd have 3x squared h plus 3xh squared plus h cubed. So that is effectively what x plus h quantity cubed is. And what I'm going to do then is I'm going to replace this expanded form back into the formula up here. So let's go for it. I would now have equals, the limit as h approaches 0. This is going to be long and nasty, but let's get through it. It would be x cubed plus 3x squared h plus 3x h squared plus h cubed. So that's what that first blue part is. I still have to, give me 1 second, I still have to subtract off that x cubed. So if I can put it in parentheses to help you see where it's coming from. This is what I just did right there. And this is all over h. Look what happens in the numerator. The x cubes canceled. So this is equal to the limit as h approaches 0 of what's left on top is 3x squared h plus 3xh squared plus h cubed. All of this is over h. What I want you to notice is, what does everything happen? Well, first of all, why am I continuing to do this? Well, just imagine if I plugged in h equals 0. The first term would be 0, second term would be 0, third term would be 0, bottom would be 0. I'm still having 0 over 0. So when do I evaluate the limit? When do I actually plug in h equals 0? The first time I can. That's the reality of the matter. And each one of these times I have not been able to plug in h equals 0 because it would have been undefined. So factor and simplify first, and then go ahead and plug in h equals 0. So I know I can pull an h out of there, so let's see this. This would be the limit as h approaches 0 of h times. We'll consider this first term, 3x squared times h. If I divide that by h, what's left? The 3x squared would be left. Plus, consider the second term, 3xh squared. If I divide that by h, what's left? It would be plus 3xh. Consider that third term, h cubed. If I divide h cubed by h, that would be plus h squared. And all of this is over h. Now I notice that I can simplify because I'm in factored form. I'm able to simplify the h's, and I'm left with the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Okay, so the question becomes, is this a limit that I can evaluate? And the answer is yes. Anywhere I see an h, I'm just going to plug in a 0. Notice again, I've been writing the limit as h approaches 0 every single one of the steps from the beginning until now, because now is the time that I can actually evaluate that limit. So this would be 3x squared plus 3x times 0 plus 0 squared. Well, 3x times 0 is 0, 0 squared is 0, so I'm left with, quite simply, 3x squared. Whew, a lot of work, but that's what it is, using the definition of derivative. And again, the whole entire point of this section is, let's do the work now so we can notice the pattern. Once we notice the pattern, we no longer need to do the limit as h approaches 0. So let's come back up to our list here, and I have 3x squared is the derivative of x cubed. Okay, so the question is, do you notice a pattern? I'm going to rewrite this a little bit to try to help pull it out of you a little bit to see if you notice the pattern. So the derivative with respect to x of x to the 1, which is just x, is really the same thing as 1x to the 0. Because remember, anything raised to the 0 power is 1. Likewise, the derivative with respect to x of x squared would be 2x to the first power. That's what 2x is, just written a little different. And the derivative with respect to x of x cubed is equal to 3x squared. So I want you to step back and take a look at that for a moment. Do you notice what's going on? Can you guess what the derivative of x to the 10th is? First of all, can you imagine doing x to the 10th? Think about when we were doing x cubed. So we would have x plus h to the 10th. So when we FOILed out 3 of these things, we'd have to be FOILing out 10 of these things. It would take forever to do that. It would be an absolute train wreck. What would happen if we did that? The limit as h approaches 0 of f of x plus h minus f of x all over h for x to the 10th. Well, we'd have 2 pages of work, and at the end of the day, what would we come up with? The answer is 10x to the 9th. Hopefully you were able to guess that. And let's look at more in general. Doesn't matter what the power is. What do you do when it's x to the n, where n is any number? You drop the power. You keep x to whatever the power is, minus 1. This is called the power rule. One of, if not the most important rule of differentiation that you are going to use time and time and time again. So, what have we learned on this page? We learned that the derivative of a constant, or the derivative of any number, any constant number, is 0. And we learned that the derivative of x to any power, x to the n, is nx to the n minus 1. Drop the power in front, make it a coefficient, and then subtract 1 from the power. Again, called the power rule.